We are ready to start time at 2 o'clock Eastern Standard Time, so we will begin. First off, good afternoon. I am Jason Thomas, Project Engineer with America Makes, and your host for today's America Makes TRX webinar series. A little background on the TRX webinar series before I introduce our speaker. As America Makes continues its mission to expand and accelerate the footprint of additive manufacturing and 3D printing, this medium called the America Makes Technical Review and Exchange webinar series was created. By creating this platform, it allows the additive manufacturing and 3D printing community to come together and share knowledge and experience with a broader community. If you or your team are interested in presenting during the TRX webinar series, there will be a link to complete the request form at the end of our series today, or you can contact America Makes TRX webinar administrator, Jason Thomas, directly. A few important notes before we kick off the series. At the end of the presentation, there will be an opportunity for a brief Q&A session. If during the presentation you have a question, please submit it in the Q&A space on your WebEx screen, and we will ask it during the Q&A session. We will do our best to get to all the questions. Today's webinar is on qualification and certification guidance for additive products in civil aviation and medical device industries. Without further ado, it is my pleasure to introduce Lauren D. Isley from NTS. NTS is a North American testing group that assists in qualification and certification testing in all industries for exposures to environmental and mechanical stresses. NTS can simulate it all. Additive manufacturing products must meet the same performance requirements at the industry for which they are targeted. Learn about the full NTS capabilities and how to contact us for future testing requirements. Okay, Lauren, I will now turn it over to you and your team.
Thank you, Jason. Good afternoon. This is Lauren Isley. I'm a testing consultant for NTS now after spending 35 years here as an AE, division manager, and various other positions. As you can see, NTS is a North American testing group, assisting qualification for certification in all industries for exposure to environmental and mechanical stresses. Additive manufacturing products must meet the same performance requirements as the industry for which they are targeted. In other words, whatever product you manufacture, it will have to meet the same requirements that manufactured with other processes have to meet those specs, and so do additive manufacturing products. You're going to you're going to learn the full capabilities of NTS. There are many additive manufacturing processes. This is a list of some of them. A very extensive list and growing. So it's a very large group of manufacturing people, and we are glad to service that industry. First thing we're going to talk about is vibration. There are many kinds of vibration, starting with sine vibration, which is resonant or rhythmic application of G levels at different frequencies, going all the way up to sometimes 3,500 hertz and starting as low as 4 or 5 hertz. Random vibration. Random is a vibration that is wide spectrum in frequency. It's conducted in a frequency domain and is controlled on the PSD levels at the various frequency bands. The overall GMS level is calculated by summing all of the vibration over the frequency range, and so that gives you the level of vibration that the part's going to see over the full frequency band. Sine on random is sine vibration riding on top of random vibration, as you might see in a helicopter with blade passing frequency, or an automobile where you got the regular random vibration of the vehicle superimposed by the piston vibrations, which will change frequency as the car speeds up, slows down. Random vibration, these are short bands of random vibration riding on a floor of random vibration, where the floor is wide range and the random spikes are very narrow bands riding above the floor. Real-time replication This is vibration that follows what happens in the field. They put sensors on the vehicles or the aircraft or the tank or whatever device you've got to try and simulate, and it measures that acceleration, displacement, and velocities, and then you have to create a profile that repeats this replication. And what happens, you have several iterations until the replication is within like 5% of coherence to the field data. Combined vibration with temperature. This is where we put the vibration machine under or beside the thermal chamber and apply thermal exposures as we're simultaneously applying the vibration. Long stroke. Short stroke is usually an inch or less. Long stroke can be feet, many feet in some cases. Like is the vibration that's associated with fuel tank sloshing. This is several feet in length to simulate the very slow frequency and low G levels that you see in a fuel tank. HALT, highly accelerated life test, where we apply thermal exposures of very high extremes, usually beyond the product specification, at a very high rate, up to 1 degree C per second. Simultaneously, we have 6-axis random vibration being applied to the table, so the part gets to see the thermal the thermal ramps, the vibration, usually separately and then combined. Environmental, we can simulate any condition on Earth or in space. Thermal exposures, hot and cold. Humidity, which is humidity up to close to 100%. Thermal and humidity, where we go through thermal ramps and humidity ramps. Settling dust, where we put the part in a chamber and we apply dust and let it settle on the part. Blowing sand and dust, the part's put in a chamber like a wind tunnel. We introduce sand and dust, can be elevated temperature, but what we're looking for is trainment of the sand and dust into the test part or an erosion of the coatings on the part. Corrosion. This is salt fog, salt spray, and this is to simulate what you might see near the seashores. Sometimes there's a acidic sea salt or salt spray. Cyclic corrosion, this is where the part is exposed to salt spray, and then the salt spray is stopped, the part is allowed to dry, and then it goes through some thermal excursions. Then when it's at high temperature, we start the salt spray again. Thermal shock, air to air. This is where we have two chambers side by side with a box going in between them. We rapidly change the box from one chamber to the other, getting a change from hot to cold in just a few seconds, and then go back the other way depending on how many cycles the specification calls for. Thermal shock, hot air to ice water with sand or salt. This is a very, very tough test, especially if you've got a part that's supposed to be sealed and it's got a fairly large gas inside of it, because you heat it up usually above 100 C and you expose it to the ice water immediately. This causes the gas inside the box to contract, creating vacuum, which if there's a leak will draw the water into the test article. The water is usually treated with a dye, which is ultraviolet light sensitive. So when the test is over, take the box apart, use the ultraviolet light and see if there was any leaks. Immersion with vacuum. This is a test that's usually used on cables, and we're looking for leaks in the cable. So we put the cable underwater and we pull a vacuum over the water, which then causes an interior pressure in the cable, and the gas or air in the cable will be forced out. Enclosure protection is water and dust. Can be both of them, one or the other. What we're looking for is the possibility of dust getting in a test article or water. Water can be a drip test simulating rain. It can be high pressure as simulated by a car wash spray. There's immersion, immersion with pressure. There's many ways that we're looking for closure protection. This is an ISO spec, typically. The next one is steam, which is high pressure, high temperature water. It impinges on the part from a high pressure hose. HAST, highly accelerated stress test. This is putting a part in a chamber, and then we expose it to humidity above 100 degrees C, which is similar to a pressure cooker. And what this does is it forces water into the test article, typically used on PCBs, printed circuit boards. Conditions for mechanical shock. First is impact, which is typically half sine or terminal sawtooth, where we apply up to 30, 40, 50 Gs, half sine, 11 milliseconds. The shock goes higher than that, up to 1,000 Gs, and then at 1,000 Gs or so, it's only a 1 millisecond or half a millisecond. So the higher the G level, the lower the duration. SRS, shock response spectrum. This is shock across the frequency range, and it's similar to random vibration. You measure this on a test part, and then you can apply it usually with an ED shaker. Sustain, centrifuge. This is how you get constant acceleration, as you might see from a rocket firing or a sled impact. So this simulates high level Gs of a constant duration, not a constant duration, but extended duration. Multiple seconds, which a drop shock can't handle, up to minutes. And then real-time replication, where we take field data, and with similar to the real-time replication for vibration, we can recreate this shock spectrum from the field data, and it usually takes several iterations until we get coherence from the real data to the test data. Fatigue and ultimate strength. This is typically mechanical or rotary fatigue. The results are plotted as stress versus cycle count. We start at a very high level of stress, so we get a low cycle count, and then we increase or decrease the stress until we get a long duration cycle count, maybe approaching 1 million cycles. Then we can plot what's referred to as an SN curve. Mechanical linear rotary ultimate. This is what is also called single cycle fatigue. We apply stress, either rotary or linear, until we get a failure. And that the results are plotted as stress versus the failure deflection. Combined linear and rotary fatigue. This is applied to parts that get both linear and rotary tests on them, like the flywheel in an automobile, where we have it's mounted on the crankshaft, so we have linear forces coming in, and then we have the rotary forces coming in, like from the starter motor. Fluid fatigue. This is pressure pulsing, very important, especially in the aircraft industry, where the pressures are rather high, and typically it's at elevated temperature. So we apply pressure pulses, and the specification usually indicates the pressure and number of cycles it has to pass. Fluid temperature and pressure. This is for manifolds, hoses, heat exchangers. These all can see high temperatures and high pressures. Can be pressure pulses, can be constant pressure for proof pressure, similar to that. Chemical exposure. The list here is typically for automobiles. So you can see most of these are automobile fluids. For the aircraft industry, we would have to add the ATF, the special hydraulic parts, the hydraulic fluids like Skydrol, which can be very corrosive. And the materials can be applied either by complete immersion, spraying, wiping. We don't recommend spraying for anything that's flammable, because you could make a flammable mixture in a hurry, and a spark could hurt everybody.
Thank you, Lauren. We will now head into the Q&A session. If you have a question for Lauren and haven't done so already, please type it into the chat box. I do have a few questions here. All right, the first question, is the qualification certification process different for products made through additive processes versus products made through traditional processes?
No, the quality cert process is the same for FAA, DOD, FDA, ASME, ISO, etc. The test standard and certification process for each industry will remain the same, for now at least. But the difference in basic composition physics of the additive versus traditional products may cause different results when tested to the same standards. Now, additive manufacturing is got lots of people working on process specifications because there's a lot of different processes, and you can see with some of these additive manufacturing processes, especially where we're depositing metals, the composition of the metal is going to make a big difference on the final product. So those all have to be controlled by processes. So they're working on that right now. For instance, American Society of Mechanical Engineers have thousands of specs for processes on materials, steels, aluminums, all those things. So the same thing's got to happen with additive manufacturing.
All right, thank you. Let's see, we've got another question here. What types of tests present the greatest challenges for additive products versus traditional products?
Okay, tests for especially harsh environments are tough on additive products. NTS experience in testing for temperature, pressure, flow, vibration, impact, fire, chemicals, etc. have shown great variabilities in results. So it's going to depend on which industry and which one of these processes or test schedules that you need to run to get your part qualified.
Okay, and let's see, what is resonant dwell vibration?
Resonant dwell vibration is sinusoidal vibration at resonant frequency for a fixed amount of time or number of cycles. Vibration frequency is determined by a sinusoidal sweep where the input vibration acceleration is compared to the response acceleration. And resonance being where the ratio of the two signals is maximum. That's the resonant frequency, and that's where you apply resonant testing.
All right, thank you very much, Lauren. So this will wrap up today's TRX webinar series. I would like to thank Lauren. If you have any further questions for Lauren, please reach out to him directly at the excuse me, at the address on the screen. And there will be a post-webinar survey going out to all those who participated. We do really appreciate the time you take to provide American Makes feedback so we may continue to improve and strengthen the additive community. And a reminder that if you think you or your organization would be interested in sharing on the TRX webinar series, please fill out the form that follows the presentation or reach out to myself, Jason Thomas, at jason.thomas@ncdmm.org. Thank you very much.